Path tracing is really simple. You shoot a ray from the camera into your scene, bounce the ray a few times, and based on what it hits, you color the pixel. For the best results, you do this multiple times for each pixel. Simple. But simple does not mean fast. Most rendering engines bounce each ray 8 to 12 times and can repeat this process anywhere from 32 to over 4,096 times per pixel. When rendering 4K images for movies or video games, the compute power needed quickly balloons. Even today, highly optimized render farms take hours to render a single frame. Take Toy Story 3 for example, which averaged about 7 to 11 hours per frame for roughly 140,000 frames. That being said, without modern algorithmic optimizations, movies like Toy Story would be nearly impossible to render. One of the most common of these optimization techniques is the use of data structures called bounding volume hierarchies, or BVHs for short. BVHs belong to a family of optimizations known as acceleration structures. An acceleration structure is a data structure, usually containing scene data, whose purpose is to speed up the rate at which a ray can traverse a 3D scene. More specifically, BVHs allow rays to more efficiently query triangles in the scene for a collision. Without an acceleration structure like a BVH, when a ray traverses a scene, it has to sequentially check every triangle within the scene for an intersection. In many path-traced scenes, the number of triangles can range from billions to trillions, making this form of scene traversal extremely slow. This is exactly the problem BVHs attempt to solve. Believe it or not, a BVH is a very simple data structure to visualize. It's effectively a tree where each node has anywhere from 2 to 8 children or no children, in which case it's a leaf node. When a mesh is loaded into memory, a bounding box is made to encompass the entire mesh. Then, within that bounding box, 8 smaller bounding boxes are made for each quadrant of the mesh. Then, within each of these sub-volumes, 8 more bounding volumes are made. This process recursively repeats until a maximum depth is reached. Now the mesh's triangles each lie within one of the bounding box's leaf nodes. There are more optimal ways to construct a BVH so that dead space is minimized, but for this video, we'll keep the example simple for the sake of time. When a ray traverses the scene, instead of checking each triangle for a collision, the ray checks each mesh's root level bounding volume for an intersection, usually with something like an AABB intersection check. If the ray intersects a volume, then it checks each of the volume's children for an intersection. The ray recursively checks the children of each bounding volume intersection until it reaches a leaf node. Then, the ray checks only the triangles within the leaf node for an intersection. This data structure reduces the time complexity for ray triangle intersection from O of n to O of log n. BVHs, however, are not only useful for path tracing and can be used for really any form of shape-to-shape intersection. For example, some physics engines use BVHs to check for mesh collisions. BVHs are also extremely useful in voxel-based software since voxels naturally adhere to a box-like structure. Bounding volume hierarchies are just one of many popular acceleration structures within 3D rendering, but it alone is a strong starting point when looking to optimize a rendering engine. I implemented a BVH in my previous OpenGL path tracing project for this very purpose.